Welcome to Sleepy Science Student, where we explore the cosmos, one gentle breath at a time. Tonight, we're going on a slow, peaceful journey to a world that has captured human imagination for centuries. Mars, the red planet. It's a place of rust-colored deserts, towering volcanoes, ancient riverbeds, and perhaps, one day, a second home for humanity. I hope this video isn't too interesting, though if it does happen to keep you awake, at least you'll be learning something fascinating about our neighboring world and humanity's dreams of touching its rusty surface. Not the worst way to spend a sleepless night. Before we drift toward Mars together, I'd love it if you gave this video a like, and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow and means more curious minds can find their way to these gentle explorations of science and space. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in London at midnight, gazing up at a sky where Mars might be twinkling, or listening from a hammock in Melbourne at noon while the afternoon sun warms your face? Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe, united by curiosity and the need for peaceful learning. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like the thin Martian wind sweeping across ancient plains. Let your shoulders relax. Let your breath slow. And as we begin this gentle voyage to the red planet, remember, this video is for educational and relaxation purposes only. It's not intended as medical advice, a guide for building actual spaceships, or a promise that you'll be colonizing Mars anytime soon, though dreaming about it is always encouraged. Ready? Let's begin. For thousands of years, humans have looked up at the night sky and noticed something unusual. Among the steady, twinkling stars, there were a few bright points of light that seemed to wander. They moved slowly across the constellations, tracing paths that ancient observers found both puzzling and captivating. One of these wanderers had a distinctive color. It glowed with a reddish hue, the color of rust, of dried blood, of fire. The Greeks called it Ares, after their god of war. The Romans renamed it Mars, and we've been fascinated by it ever since. Mars is not just any planet. It's our neighbor, our closest planetary companion beyond the moon. On a clear night, when Mars is at opposition, meaning it's on the opposite side of Earth from the sun, you can spot it with your naked eye. It doesn't twinkle like stars do. Instead, it shines with a steady, rusty light. That steadiness happens because Mars is close enough that it appears as a tiny disk in our sky, not just a point of light. The light from all parts of that disk averages out, creating that calm, unwavering glow. You might think Mars looks red because it's hot, but actually, Mars is quite cold. The red color comes from iron oxide rust, covering much of its surface. Imagine a world where nearly everything is covered in a fine layer of rust. Dust, like an old forgotten tool left out in the rain for decades. That's Mars. It's a planet that, in some ways, looks like it aged too quickly, oxidizing in the harsh environment of space. But here's where things get interesting. Mars wasn't always the cold, dusty world we see today. Scientists have found compelling evidence that Mars once had liquid water flowing across its surface. Not just puddles or small streams, but rivers, lakes, perhaps even oceans. The planet had a thicker atmosphere, a warmer climate, and conditions that might have been suitable for life. What happened? Why did Mars transform from a potentially habitable world into the frozen desert we observe now? That's one of the great mysteries we're going to explore together, slowly and gently, as we wander through the Martian landscape. Let's pause for a moment and appreciate what it means to study Mars. We're looking at a world that's, on average, about 140 million miles away from Earth. That distance changes as both planets orbit the Sun, sometimes bringing Mars as close as 34 million miles, other times pushing it as far as 250 million miles away. Even at its closest, Mars is roughly 140 times farther from you than the Moon. And yet, we've managed to send spacecraft there. We've landed rovers that trundle across its surface, cameras that photograph its canyons, and instruments that analyze its rocks. We've turned this distant red wanderer into a place we can explore, a world we can begin to understand. The journey to Mars takes months. Our fastest spacecraft have made the trip in about 7 months, though most missions take closer to 9. Imagine spending that long in a tin can, hurtling through the void, knowing that a thin sheet of metal is all that separates you from the deadly vacuum of space. Yet people dream of making this journey. They volunteer for one-way missions. They dedicate their lives to figuring out how humanity might one day walk on Martian soil, build habitats under Martian skies, and perhaps, just perhaps, make Mars a second home. Why Mars? Of all the planets in our solar system, why does Mars capture our imagination so completely? Part of it is proximity, of course. Mars is close enough to reach with current technology, but there's more to it than that. Mars is not just another planet. It's a world with seasons, polar ice caps, dust storms, and canyons that dwarf anything on Earth. It's a place that's similar enough to Earth to feel familiar, yet different enough to feel alien. It's a world that might have harbored life in its ancient past, and perhaps, with our help, might harbor life again in its future. As you lie there, breathing slowly, imagine standing on Mars, the sky above. You isn't blue. It's a butterscotch yellow during the day, fading to a soft blue around the setting Sunday. The gravity is only 38% of what you feel on Earth, so you'd weigh less than half your normal weight. A jump that might lift you a foot off the ground here would send you sailing nearly 3 feet high on Mars. The air is so thin you couldn't breathe it. It's mostly carbon dioxide, with a pressure less than 1% of Earth's atmosphere. You'd need a spacesuit just to stand on the surface. And the cold, oh, the cold would seep through any crack or flaw. Because on average, Mars has a temperature of about -80 degrees Fahrenheit. But for all its harshness, Mars is strangely beautiful. The rocks are scattered across plains that stretch to the horizon. Ancient volcanoes rise up in the distance, their peaks so tall they pierce the thin atmosphere. Canyons cut through the landscape like scars, revealing layers of history in their walls. And if you time it right, you might witness one of Mars's famous dust storms, watching as the wind, thin but persistent, lifts dust particles and paints the entire planet in shades of amber and ochre. This is where we're going tonight. Not in a spaceship, but in thought. We're going to explore Mars, slowly, gently, one fascinating detail at a time. We'll wander through its geology, drift through its atmosphere, float over its ancient riverbeds, and consider what it might mean for humans to one day call this rusty world home. You don't need to remember everything. You don't need to stay awake. Just let the story of Mars unfold around you, like dust settling after a storm, soft and inevitable. And so, our journey begins. Let's talk about the planet itself, its size, its structure, its place in the cosmic neighborhood we call the solar system. Mars is smaller than Earth, not by a little bit, but significantly. If Earth were a basketball, Mars would be roughly the size of a softball. The radius of Mars is about 2,106 miles, compared to Earth's 3,959 miles. That means Mars has about half the diameter of our planet. But here's where it gets interesting. Because volume increases with the cube of the radius, Mars has only about 15% of Earth's volume. It's not just a bit smaller, it's substantially smaller. You might think this means Mars is a lightweight, a planetary featherweight compared to our robust Earth. And in a sense, you'd be right. Mars has only about 11% of Earth's mass. If you could somehow place Mars on a cosmic scale next to Earth, you'd need about 9 Mars-sized planets to balance out one Earth. This lower mass has profound implications for everything about Mars: its gravity, its ability to hold onto an atmosphere, even its internal heat and geological activity. The gravity on Mars, as we mentioned, is about 38% of Earth's gravity. This isn't just a fun fact for calculating how high you could jump. It has real consequences. Lower gravity means that atmospheric particles move faster at any given temperature. It's a bit like holding onto a bunch of helium balloons on a windy day versus a calm day. The wind, or in this case, solar wind, and the higher velocities of atmospheric particles makes it easier for gases to escape into space. Over billions of years, this has been one of the factors contributing to Mars losing most of its atmosphere. Let's drift deeper into Mars's structure. Like Earth, Mars is differentiated, meaning it has distinct layers. At the center lies a core, probably made of iron, nickel, and sulfur. For a long time, scientists debated whether Mars's core was solid or liquid. Recent data from NASA's InSight lander, which measured Mars quakes, yes, Mars has quakes, suggests the core is at least partially liquid. This core has a radius of somewhere between 900 and 1,200 miles, quite large relative to the planet's overall size. Above the core sits the mantle, a thick layer of silicate rock, unlike Earth's mantle, which is vigorously convecting and driving plate tectonics. Mars's mantle is relatively quiet now. It might have been more active billions of years ago, when Mars was hotter. But today, it's cooling slowly, like a pot of soup left on the counter, long after dinner is done. This cooling has implications for Mars's geological history, as we'll explore in a bit. The outermost layer is the crust, the rocky shell that we see when we look at Mars. The Martian crust is thicker than Earth's, ranging from about 25 to 45 miles deep. In some regions, particularly under the massive Tharsis volcanic region, it might be even thicker. This thick crust acts like a good insulator, trapping heat inside the planet and allowing certain regions to stay warm enough for volcanic activity longer than they might otherwise. Now, let's talk about Mars's orbit and its day. Mars takes about 687 Earth days to complete one orbit around the Sun that's nearly 2 Earth years. So a Martian year is almost twice as long as ours. But a Martian day, called a sol, is remarkably similar to an Earth day. One sol lasts about 24 hours and 37 minutes. If you were living on Mars, you'd find the day-night cycle comfortingly familiar, though everything would slowly shift forward by those extra 37 minutes. Your sleep schedule would drift gradually if you tried to stick to an Earth-based clock. Mars's orbit is more elliptical than Earth's. While Earth travels in a nearly circular path around the Sun, Mars's orbit is noticeably elongated. This means Mars gets significantly closer to the Sun at some points in its orbit and farther away at others. The difference in distance affects how much solar energy Mars receives, which in turn affects its seasons and climate. When Mars is closest to the Sun, a point called perihelion, it receives about 40% more sunlight than when it's farthest away at aphelion. This creates some dramatic seasonal variations, especially in the southern hemisphere. Speaking of seasons, yes, Mars has them. The planet's rotational axis is tilted at about 25 degrees, very similar to Earth's 23.5-degree tilt. This axial tilt is what gives both planets their seasons, as different hemispheres lean toward or away from the Sun throughout the year. However, because of that elliptical orbit, seasons on Mars are not equal in length. Spring in the northern hemisphere lasts about 7 months, while autumn lasts only 4 months. The southern hemisphere experiences even more extreme variations, with summers that are short but intense, and winters that are long and brutally cold. Take a breath. Let all of this settle gently in your mind. The size, the mass, The gravity, the structure, the orbit. Mars is a world of contrasts and extremes. Yet it's governed by the same physical laws that govern Earth. It's simultaneously familiar and alien, a place where the fundamentals of planetary science play out in ways both similar to and different from our home world. Let's pause and consider what this all means. Mars is a small planet that cooled relatively quickly. Its lower mass meant it couldn't hold onto its atmosphere as effectively as Earth. Its slower rotation and smaller size meant it couldn't maintain a strong magnetic field, something we'll talk about more later. All of these factors combined to create a world that started out with promise but ended up cold, dry, and seemingly lifeless. But here's the thing. Mars isn't dead. It's dormant. There's still water ice locked away in the polar caps, and beneath the surface, there's still geological activity, albeit much slower than Earth's. There are still dust storms that can envelop the entire planet. Mars is a world in a state of slow decay. Perhaps, but it's not a corpse. It's more like a sleeping giant, quiet, but not gone. And understanding its anatomy, its structure, its orbit, its physical properties, is the first step in understanding why it became what it is, and what it might become if humans decide to make it a second home. You might be wondering about Mars's moons. Unlike Earth, which has one large moon, Mars has two tiny moons, named Phobos and Deimos, fear and dread, named after the sons of Ares in Greek mythology. Phobos is the larger of the two, with a diameter of about 14 miles. Deimos is even smaller, at about 8 miles across. Both are irregularly shaped, more like potatoes than spheres. Scientists believe they're probably captured asteroids, snared by Mars's gravity at some point in the distant past. Phobos is particularly interesting because it's gradually spiraling inward toward Mars. In about 50 million years, a blink of an eye, in geological terms, Phobos will either crash into Mars or break apart and form a ring system around the planet. Imagine that. Mars with rings, like a miniature Saturn, though much less grand. For now, though, Phobos orbits Mars about 3 times per Martian day, rising in the west and setting in the east, the opposite of what we see with our moon. These moons don't have much influence on Mars. They're too small to create significant tides or stabilize Mars's axial tilt the way our moon does for Earth. They're more like cosmic decorations, too small witnesses to Mars's long history. But they might prove useful for future Mars explorers. Phobos, in particular, could serve as a staging area or observation post, a place where astronauts could study Mars from a safe distance before descending to the surface. As you let your mind wander through this information, imagine Mars floating in the darkness of space. It's not just a point of light anymore, but a world, a sphere with layers and structure, with moons keeping it company, with an elliptical orbit that carries it closer to and farther from the Sunday. It's a place with days and nights, seasons and storms, history, and perhaps even a future. This is the stage upon which the rest of our story unfolds. Mars, the red planet, smaller than Earth but no less fascinating. A world shaped by the same forces that shaped our own planet, yet which took a different path. Understanding Mars's basic anatomy helps us appreciate everything else about it, its surface features, its atmosphere, its climate, and its potential as a destination for humanity. Now that we've established what Mars is, its size, structure, and place in the solar system, let's explore what Mars looks like. Let's drift across its surface and discover the geological wonders that make Mars one of the most intriguing destinations in our cosmic neighborhood. If you could hover above Mars and look down at its surface, the first thing you'd notice is the color. It's red, not uniformly, but in shades ranging from rusty orange to dark brown, with patches of darker rock and lighter dust. This red color, as we mentioned earlier, comes from iron oxide rust. The surface of Mars is rich in iron, and over billions of years, that iron has oxidized, giving the planet its distinctive hue. It's as if Mars rusted in place, a testament to the chemical processes that have slowly transformed its surface. But Mars is not just a featureless rust ball. Far from it. The planet has some of the most dramatic geological features in the entire solar system. Let's start with something truly remarkable. Olympus Mons, the largest volcano in the solar system. This mountain is absolutely massive. It rises about 13.6 miles above the surrounding plains, nearly 2.5 times the height of Mount Everest. But here's what makes it even more impressive. It's not a steep, towering peak. Instead, Olympus Mons is a shield volcano, meaning it has gentle slopes that spread out over an enormous area. The base of this volcano is about 370 miles in diameter. If you were standing at the center, the slopes would extend beyond the horizon in every direction. Imagine trying to climb Olympus Mons. The slopes are so gradual, typically only 2 to 5 degrees, that you'd barely notice you were going uphill. You could walk for days, slowly ascending, and never realize you were climbing the tallest mountain in the solar system until you looked at a map or noticed the air pressure dropping. Actually, wait, the air pressure on Mars is already so low that changes would be hard to detect without instruments. But you get the idea. Olympus Mons is a giant, but a gentle one, at least in terms of its slopes. This volcano probably formed over hundreds of millions of years, with countless eruptions slowly building it up layer by layer. On Earth, plate tectonics would move the crust over a volcanic hotspot, creating chains of volcanoes like the Hawaiian Islands. But Mars doesn't have active plate tectonics. The crust just sits there, and if magma finds a weak spot, it keeps erupting in the same location, building higher and higher. Olympus Mons is the result of this process taken to an extreme. Is Olympus Mons still active? We're not entirely sure. Some studies suggest that parts of it might have seen volcanic activity as recently as a few million years ago, which in geological terms is practically yesterday. But there's no evidence of current eruptions. Olympus Mons might be dormant, quietly sleeping, waiting perhaps for some future time when Mars's interior warms enough to send magma bubbling up once more. Or it might be extinct, its volcanic days behind it. We simply don't know yet. Olympus Mons isn't alone. Mars has an entire region called Tharsis that's home to several massive volcanoes. 3 of them, Arsha Mons, Pavonis Mons, and Ascraeus Mons, line up in a row, each rising several miles above the already elevated Tharsis Plateau. Together, these 4 giant volcanoes represent an incredible concentration of volcanic activity. The Tharsis region itself is a bulge on Mars, a massive uplift that rises about 6 miles above the average Martian surface. This bulge probably formed from the pressure of magma pushing up from below, stretching and fracturing the crust. Now, let's talk about Valles Marineris, the grandest canyon in the solar system. If Olympus Mons impresses with its height, Valles Marineris astounds with its depth and length. This canyon system stretches about 2,500 miles across Mars, roughly the distance from New York to Los Angeles. It reaches depths of up to 4 miles in some places, and in certain sections, it's as much as 125 miles wide. Compare that to the Grand Canyon, which is about 277 miles long, up to 18 miles wide, and about a mile deep. Valles Marineris makes the Grand Canyon look like a crack in the sidewalk. How did this enormous canyon form? Scientists aren't entirely certain, but the leading theory is that it's related to the Tharsis bulge. As the Tharsis region swelled upward, it stretched the surrounding crust, creating fractures and faults. Imagine pulling apart a piece of taffy at some point. It starts to thin and crack. Something similar might have happened on Mars. Once the initial fractures formed, erosion from water, wind, and perhaps landslides widened and deepened them over billions of years. Walking through Valles Marineris would be an awe-inspiring, perhaps terrifying experience. The walls of the canyon would rise up on either side of you, towering cliffs that dwarf anything on Earth. The scale would be almost incomprehensible. You could stand in the middle of the canyon and not see the walls on a hazy day because they'd be beyond the horizon. The layered rock exposed in those walls would tell the story of Mars's geological history, each stripe representing a different era, a different climate, a different version of the planet. Let's drift northward now, toward Mars's polar regions. Mars has polar ice caps, just like Earth, but these caps are different in some important ways. Earth's polar ice is mostly water ice, with some snow. Mars's polar caps are a mixture of water ice and carbon dioxide ice. In the winter, when temperatures at the poles drop to about -195 degrees Fahrenheit, carbon dioxide from the atmosphere freezes out of the air and adds a seasonal layer of dry ice to the caps. This layer can be several feet thick. In the spring and summer, this carbon dioxide ice sublimates, turns directly from solid to gas, and returns to the atmosphere. Beneath the seasonal carbon dioxide ice lies permanent water ice. The North Polar ice cap is particularly interesting. It's made primarily of water ice and is about 600 miles across. If you could melt all the ice in Mars's North Polar cap, you'd have enough water to cover the entire planet in a layer about 18 feet deep. That's not an ocean, but it's substantial. The South Polar cap is similar, though smaller and more mysterious in some ways. The polar caps have beautiful spiral patterns etched into them. These troughs and ridges spiral outward from the center like a cosmic pinwheel. They form because of the interaction between ice deposition, wind patterns, and the sublimation of ice during the warmer months. The patterns are so regular and striking that they almost look artificial, as if some cosmic artist carefully carved them into the ice. Take a breath. Let's pause and think about what we've covered. Mars has volcanoes that dwarf Everest, canyons that make the Grand Canyon look tiny, and polar ice caps with spiral patterns etched by wind and sublimation. It's a world of superlatives, a place where natural processes have created features on a scale that humbles us, and we've barely scratched the surface. Now, let's talk about the dichotomy of Mars, one of its most puzzling features. If you look at a map of Mars, you'll notice something odd. The northern hemisphere is much lower in elevation and smoother than the southern hemisphere. The southern highlands are ancient, heavily cratered terrain that rises several miles above the northern lowlands. This difference is so stark that scientists call it the Martian dichotomy, and explaining it has been a challenge. Why does Mars have this sharp division between north and south? Several theories have been proposed. One idea is that Mars suffered a massive impact early in its history, a collision with an object, perhaps a third the size of Mars itself. This impact would have excavated the northern lowlands, creating the dichotomy we see today. Another theory suggests that the dichotomy is the result of plate tectonics in Mars's early history, before the planet cooled and such activity ceased. A third possibility involves patterns of convection in Mars's mantle, with upwelling in some areas and downwelling in others, creating the elevation differences over time. We might never know for certain which explanation is correct, or perhaps the truth is some combination of factors. But the dichotomy is real, and it has implications for many aspects of Mars's history, including where water might have flowed and pooled billions of years ago. Speaking of water, let's talk about the evidence for ancient water on Mars. This is where things get really interesting. Mars today is a desert, a frozen wasteland where liquid water cannot exist on the surface for long. The atmospheric pressure is too low. Water would either freeze or boil away almost immediately. But the surface of Mars is covered with features that look like they were carved by flowing water. There are channels that meander across the landscape, like dried-up rivers, There are valley networks that resemble the branching patterns of tributaries feeding into larger streams. There are deposits that look like ancient lake beds. Some regions show features that could be deltas, where rivers once emptied into larger bodies of water, depositing sediment in fan-shaped patterns. All of this evidence points to one conclusion. Mars once had liquid water on its surface, probably lots of it, and for a long time. How long ago was this? The evidence suggests that Mars's wet period was primarily in its first billion years, a time we call the Noachian period, named after Noachis Terra, a heavily cratered region in the southern highlands. During this time, Mars might have had a thicker atmosphere and a warmer climate, allowing water to flow and pool on the surface. There might have been rivers, lakes, perhaps even an ocean in the northern lowlands. What happened to all that water? Some of it escaped to space, molecule by molecule, over billions of years. Some of it remains locked in the polar ice caps, and a significant amount is probably still there, frozen in the ground as permafrost, hidden beneath the rusty surface. We'll talk more about this hidden water later, because it's crucial to understanding Mars's potential as a future home for humans. The landscapes of Mars tell a story. They speak of a world that was once more active, more dynamic, more alive in a geological sense. The massive volcanoes suggest an interior that was once much hotter, capable of producing vast quantities of magma. The canyons and valleys hint at tectonic forces and erosion on a grand scale. Channels whisper of a time when water flowed freely across the surface, and the polar caps, with their spiral patterns, remind us that Mars still has active processes, still has a climate and seasons, even if they're very different from Earth's. As you lie there, breathing slowly, imagine yourself floating above Mars, watching these landscapes pass beneath you. The towering volcanoes, the yawning canyons, the smooth northern plains, the cratered southern highlands, the gleaming polar caps. Each feature is a chapter in Mars's autobiography, a clue to its past and a hint about its future. Mars is not just a ball of rust, it's a world with a story, a planet that has lived through eras of heat and cold, wet and dry, geological fury and quiet dormancy, and we're just beginning to read that story. Let's continue our gentle exploration by looking at what happened to Mars's atmosphere, the invisible blanket that once wrapped the planet in warmth, but has since been mostly stripped away. Imagine, for a moment, an invisible blanket wrapping around a planet, keeping it warm, protecting it from harmful radiation, providing the medium for weather and wind. That's what an atmosphere does. Earth's atmosphere is thick enough to create the pressure we need to breathe, to keep liquid water stable on the surface, to shield us from the worst of the sun's radiation. But Mars's atmosphere is different. It's thin, so thin that it's almost not there at all. The atmospheric pressure on Mars averages about 600 pascals. If that number doesn't mean much to you, here's a comparison. Earth's atmospheric pressure at sea level is about 101,325 pascals. That means Mars's atmosphere has less than 1% of the pressure we experience on Earth. It's roughly equivalent to the atmospheric pressure you'd find at an altitude of about 22 miles above Earth's surface, well into what we consider space. No human could survive in such low pressure without a spacesuit. This thin atmosphere is composed almost entirely of carbon dioxide, about 95%. There's also nitrogen, 2.8%, argon, 2%, and trace amounts of oxygen, carbon monoxide, water vapor, and other gases. So while there is oxygen on Mars, there's not nearly enough to breathe. You'd need to bring your own air or produce it from the Martian environment, perhaps by splitting carbon dioxide into carbon and oxygen. But Mars's atmosphere wasn't always this thin. We know this because of multiple lines of evidence. First, there are those ancient river channels and lake beds we talked about. Liquid water cannot exist at Mars's current atmospheric pressure and temperature. It would sublimate or freeze almost instantly. For rivers to have flowed, Mars must have had a thicker atmosphere that created higher surface pressure and warmer temperatures. Second, certain isotope ratios in Mars's atmosphere suggest that the planet has lost a significant fraction of its original atmosphere to space. The lighter isotopes preferentially escaped, leaving behind a higher concentration of heavier isotopes, a signature of atmospheric loss. So what happened? How did Mars go from a world with a potentially habitable atmosphere to the thin-aired planet we see today? The answer lies in magnetism, or more specifically, the lack of it. Earth has a strong magnetic field generated by its liquid iron core. As the molten iron swirls and convects, it creates electric currents, which in turn generate magnetic fields. These fields extend far out into space, forming what scientists call the magnetosphere. This magnetic shield protects Earth's atmosphere from the solar wind, a constant stream of charged particles flowing out from the sunday. When those particles hit Earth's magnetosphere, they're deflected around the planet, like water flowing around a rock in a stream. Without this protection, the solar wind would gradually strip away Earth's atmosphere. Mars, however, doesn't have a global magnetic field, at least not anymore. Evidence suggests that Mars once did have such a field, probably during its first few 100 million years, when its core was hotter and more dynamic. But as Mars cooled, remember, it's smaller than Earth and lost its internal heat more quickly. Its core became less active, the convection slowed, the magnetic dynamo sputtered and died, and Mars's global magnetic field vanished. Without that protective magnetic shield, the solar wind began to interact directly with Mars's atmosphere. The charged particles from the Sun slammed into atmospheric molecules, transferring energy and momentum. Some molecules gained enough energy to escape Mars's gravity entirely. Others were ionized, their electrons stripped away, and then picked up by the magnetic fields carried by the solar wind and dragged off into space. Slowly, over hundreds of millions of years, Mars's atmosphere was eroded away. Mars's fate might have been sealed billions of years ago when its core cooled just enough to shut down the magnetic dynamo. That single change, the loss of a magnetic field, led to the gradual stripping of the atmosphere, which led to cooling and the loss of liquid surface water, which led to the cold, dry planet we see today. It's a reminder of how interconnected planetary systems are, how one change can cascade through the entire system. Now, Mars does have some remnant magnetic fields. Certain regions of the crust, particularly in the southern highlands, have strong, localized magnetic fields frozen into the rocks. These crustal magnetic fields tell us that Mars once had a global field strong enough to magnetize the crust, and that some of that magnetization has persisted to this day. These patches of magnetic field provide a glimpse into Mars's magnetic past, like fossils of an ancient era. Even with its thin atmosphere, Mars still has weather. Yes, weather. It has seasons, clouds, wind, and even dust storms. Let's talk about those dust storms, because they're one of Mars's most dramatic phenomena. Martian dust is incredibly fine, much finer than sand on Earth. Individual dust particles are typically only a few micrometers across, about the size of particles in cigarette smoke. These particles are easily lifted by the wind, and once aloft, they can stay suspended in the thin atmosphere for long periods. Small dust devils spinning columns of dust are common on Mars, particularly during the warmer months. But sometimes, dust storms on Mars grow to enormous proportions. Local storms can expand and merge, eventually covering regions, hemispheres, or even the entire planet. These global dust storms happen every few Martian years, though not on a perfectly predictable schedule. When one occurs, the entire planet can be enveloped in a thick haze of suspended dust. The sky darkens, the temperature equalizes across the planet, and the sun becomes just a dim glow in the butterscotch sky. You might remember a global dust storm that occurred in 2018. It was this storm that eventually led to the end of NASA's Opportunity rover. which had been exploring Mars for nearly 15 years. The storm blocked out so much sunlight that Opportunity's solar panels couldn't generate enough power. The rover went into hibernation and never woke up. It's a poignant reminder of how harsh the Martian environment can be, even for our most durable robots. Take a breath, slowly. Think about the wind on Mars. It's thin, but persistent. It shapes dunes, carves rocks, lifts dust into the sky. The wind on Mars whispers rather than roars, but it has had billions of years to shape the landscape, and its effects are everywhere. Mars also has clouds, though they're different from Earth's clouds. Most Martian clouds are composed of water ice, similar to cirrus clouds on Earth. They tend to form at high altitudes and in certain seasons. There are also clouds made of carbon dioxide ice, particularly at the poles during winter. These clouds are similar to the polar-type stratospheric clouds we occasionally see on Earth, though on Mars they're more common. One particularly interesting phenomenon is something called the aphelion cloud belt. When Mars is farthest from the Sun in its orbit, at aphelion, a belt of water ice clouds forms around the equator at altitudes of about 12 to 19 miles. These clouds persist for several months, creating a hazy ring around the planet's middle. Why does this happen? The exact mechanism is still being studied, but it's thought to involve the transport of water vapor from the southern polar region to the equatorial zone, combined with the cooler temperatures at aphelion. The temperature on Mars varies greatly, both across the planet and throughout the day. At the equator, during summer, daytime temperatures can reach a relatively balmy 70 degrees Fahrenheit, but at night, those temperatures can plummet to minus 100 degrees Fahrenheit, or colder. That's a swing of 170 degrees in a single day. At the poles in winter, temperatures can drop below minus 200 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the air. These extreme temperature swings happen because Mars's thin atmosphere can't hold heat the way Earth's does. On Earth, our thick atmosphere acts like a blanket, absorbing heat during the day and releasing it slowly at night, moderating temperature changes. Mars's atmosphere is too thin to do this effectively. Heat radiates back into space almost as soon as the sun sets, causing temperatures to drop rapidly. You might be wondering about the day-night temperature swings if you were standing on Mars. If you were in a spacesuit on the equator at noon, the sun-facing side of your suit might warm up significantly from solar radiation, but step into the shadow, even for a moment, and you'd immediately feel the cold. There's no thick atmosphere to carry heat around, so temperature differences can exist over very short distances. It's a strange environment, one where local conditions can vary dramatically depending on factors like time of day, latitude, season, and even whether you're in sun or shade. The thin atmosphere has another consequence. Cosmic rays and solar radiation can reach the surface with little attenuation. On Earth, our thick atmosphere absorbs and scatters much of this harmful radiation. On Mars, the radiation exposure is much higher. Astronauts on Mars would need to shield themselves, perhaps by living underground or using thick walls of Martian regolith, soil, to block radiation. This is one of the challenges we'll have to solve if we want to live on Mars long term. As we drift through this section, it's worth pausing to appreciate the delicate balance required for a planet to maintain a thick, protective atmosphere. It requires the right size, the right distance from the sun, a magnetic field to fend off the solar wind, and perhaps even plate tectonics to recycle atmospheric gases. Mars had some of these ingredients early on, but not all, and not for long enough. The result is the cold, thin-aired world we see today. But here's a thought that might keep you awake or gently lull you to sleep, depending on your perspective. Even though Mars lost most of its atmosphere, it might be possible to give it a new one. This idea, called terraforming, involves deliberately modifying Mars's environment to make it more Earth-like. Could we thicken Mars's atmosphere again? Could we warm the planet and bring liquid water back to its surface? These are questions, we'll explore later in our journey. For now, just let the idea float in your mind, like a dust particle suspended in the Martian breeze. The atmosphere of Mars, thin, cold, and mostly carbon dioxide, is both a challenge and an opportunity. It's a challenge because it makes Mars inhospitable to life as we know it. But it's an opportunity because even in its thinness, it provides resources we could potentially use. Carbon dioxide can be split into oxygen for breathing and carbon for building materials. The thin air can still carry heat, however, inefficiently, and the dust that fills the sky during storms could be a nuisance. But it's also a reminder that Mars is still an active, dynamic world. Now, let's talk about something even more exciting: the water on Mars. Not the ancient water that once flowed in rivers, but the water that's still there, frozen beneath the surface, locked in the polar caps, perhaps even existing as liquid in certain underground locations. Water is essential for life, essential for human colonization, and understanding where it is and how to access it is crucial for Mars's future. Water is life. It's not just a poetic statement, it's a biological fact. Every form of life we know requires water to survive. Water is the medium in which biochemical reactions occur. It's the universal solvent, capable of dissolving more substances than any other liquid. Where there's water, there's at least the potential for life. So the question of water on Mars is not just scientifically interesting. It's fundamentally important to understanding whether Mars ever harbored life, and whether it could support human colonization in the future. We know Mars has water. The polar caps alone contain vast quantities of water ice. But the real question is, where else is water hiding on Mars, and in what forms? Over the past few decades, spacecraft and rovers have revealed that Mars is actually much wetter than it appears at first glance. Let's start with the obvious: the polar ice caps. We've already mentioned that these caps are a mixture of water ice and seasonal carbon dioxide ice. But let's dig a little deeper. The North Polar Cap, during summer when the dry ice has sublimated away, is almost pure water ice. Measurements suggest it contains about 2.85 million cubic miles of water ice. That's roughly half the volume of the Greenland ice sheet on Earth. If you could melt all of it, you'd have enough water to create a global ocean on Mars, about 18 feet deep. The South Polar Cap is more complicated. It also contains substantial water ice, but it's partially covered by a permanent layer of carbon dioxide ice. Even in summer, this dry ice layer is several feet thick and sits on top of the water ice beneath. Why doesn't this carbon dioxide ice sublime away like it does at the North Pole? The temperatures at the South Pole stay cold enough, year-round, to keep some of it stable. Mars's elliptical orbit plays a role here. Southern winters are longer and colder than northern winters. Both polar caps have beautiful layered structures. If you could drill down into them, you'd see alternating layers of ice and dust, like tree rings recording Mars's climate history. These layers form because of variations in Mars's orbital parameters over time. Mars's axial tilt varies more than Earth's does. It can wobble between about 15 and 35 degrees over timescales of millions of years. These changes affect how much sunlight reaches the poles and where dust and ice accumulate. Each layer in the polar ice tells a story of a particular climatic period. But the polar caps are just the visible tip of the Martian ice reservoir. There's far more water hidden beneath the surface in the form of ground ice permafrost. Numerous observations have confirmed that much of Mars's subsurface, particularly at mid to high latitudes, is rich in water ice. This ice is mixed with the regolith, sometimes forming nearly pure ice layers just a few feet below the surface. How do we know this? Several ways. One method involves looking at fresh impact craters. When a meteorite slams into Mars, it excavates material from beneath the surface and throws it onto the surrounding plains. Sometimes these ejecta deposits contain bright material that disappears over the course of weeks or months. That bright material is almost certainly water ice, exposed by the impact and then sublimating away in the thin atmosphere. It's like Mars revealing its secrets accidentally every time something hits it. Another way we've detected subsurface ice is with instruments that can probe beneath the surface. The Mars Odyssey spacecraft carries a gamma-ray spectrometer that can detect hydrogen in the top meter or so of Mars's surface. Hydrogen is a component of water, so high hydrogen concentrations indicate buried ice. These measurements have shown that vast regions of Mars, particularly at latitudes above 50 degrees north and south, have ice-rich subsurface layers. In some places, the ice is so close to the surface that it's been exposed by erosion, creating features called ice scarps. These are steep cliffs where layers of nearly pure ice are visible, like geological cross-sections. The HiRISE camera on NASA's Mars Reconnaissance Orbiter has photographed several of these ice scarps, revealing ice layers that extend down at least 300 feet and are probably much thicker. This subsurface ice is incredibly important for any future human missions. Water is heavy, and launching it from Earth to Mars would be extremely expensive. But if colonists can mine water ice from the Martian subsurface, they can melt it, purify it, and use it for drinking, growing crops, and producing oxygen. They can also split water into hydrogen and oxygen and use those elements as rocket fuel. Subsurface ice could be one of the most valuable resources on Mars. Take a moment to imagine this. Picture yourself standing on Mars, looking at what seems like a barren, dry landscape. But just a few feet beneath your boots, there's ice, billions upon billions of gallons of frozen water, waiting. It's like standing in a desert while walking above an aquifer. The water is there, hidden, preserved by the cold and the thin atmosphere, waiting to be tapped. Now let's talk about something even more intriguing: liquid water. Can liquid water exist on Mars today? For a long time, scientists thought the answer was no. The atmospheric pressure is too low, and the temperature's too cold for liquid water to be stable on the surface. Water would either freeze or boil away almost immediately. But recent discoveries have challenged that assumption. In 2015, scientists announced evidence for seasonal flows of briny water on Martian slopes. These features, called recurring slope lineae, or RSL, appear as dark streaks that grow and fade with the seasons. They tend to appear during warm months and disappear when it gets cold. The streaks occur on steep slopes, often facing the equator, where temperatures reach the highest values. Analysis of the spectral signatures of these features suggested the presence of hydrated salts, minerals that contain water molecules. The leading theory is that these streaks are caused by briny water flowing downhill. Salt can lower the freezing point of water, allowing it to remain liquid at temperatures where pure water would freeze. It can also lower the boiling point and increase the stability of liquid water at low pressures. So, it's possible that salty water seeps out of the ground during warm periods, flows downhill, and then refreezes or evaporates when temperatures drop. However, this interpretation has been debated. Some scientists think the streaks might be caused by flowing sand or some other dry process. The truth is, we're not entirely certain. More observations and perhaps direct measurements will be needed to confirm whether liquid water is actually involved in creating these recurring slope lineae. Even more controversial is the question of liquid water beneath Mars's surface. On Earth, we have subsurface lakes and aquifers, places where liquid water exists in underground reservoirs. Could Mars have something similar? In 2018, radar data from the European Space Agency's Mars Express orbiter suggested the presence of a liquid water lake about 12 miles wide beneath the South Polar ice cap, about a mile below the surface. This discovery was exciting, but has also been questioned. Bright radar reflections that indicated liquid water could potentially be explained by other materials, like clays or salts, or perhaps it really is liquid water, kept liquid by the insulating effect of the ice above. and the presence of dissolved salts. The debate continues, and more data will be needed to settle the question definitively. The possibility of liquid water beneath Mars's surface raises profound questions. If there's liquid water, could there be life? On Earth, wherever we find liquid water, no matter how deep, how hot, how cold, how salty we find life, microbes thrive in subglacial lakes beneath Antarctic ice. They live in the crushing darkness of the deep ocean. They survive in acid mine drainage and in the hyper-arid Atacama Desert. Life is tenacious, adaptable, and seemingly able to colonize any niche where liquid water exists. Even briefly, could Mars have similar subsurface ecosystems? It's possible, though we have no evidence for it yet. If life exists on Mars today, it's probably deep underground, protected from the harsh surface conditions, eking out an existence in pockets of liquid water or moist soil. Finding such life would be one of the most profound discoveries in human history, proof that life can arise independently on different worlds, evidence that we're not alone in the universe. But let's not get ahead of ourselves. Let's bring our attention back to what we know for certain. Mars has vast quantities of water in the form of polar ice and subsurface permafrost. It may have small amounts of liquid water, either flowing on the surface seasonally or pooled beneath the ice. This water represents both a scientific target, a place to look for past or present life, and a practical resource for future explorers. Accessing this water won't be easy. Mining subsurface ice would require drilling equipment, heating systems to melt the ice, and purification processes to remove salts and other contaminants. But it's doable with current or near-future technology, and the payoff would be enormous. Water means life support. It means agriculture. It means fuel. It means the difference between a temporary outpost and a permanent settlement. As you lie there, let your mind drift to those frozen reservoirs beneath Mars's surface. Imagine the ice layers, accumulated over millions of years, holding within them the chemical records of ancient climates. Imagine the possibility of liquid water trapped in subsurface pockets, perhaps hosting microbial ecosystems isolated from the rest of the universe. Imagine future colonists drilling down, hearing the satisfying sound of drill bits breaking through ice, then pumping up water that will sustain them on this alien world. The water on Mars is not just a scientific curiosity, it's a key to the planet's past, a potential indicator of life, and a resource that could enable humanity's expansion beyond Earth. Understanding where this water is, how much there is, and how to access it is one of the most important tasks for current and future Mars missions. Now that we've explored the hidden waters, let's talk about something closely related: the search for life on Mars. If there's water, even just frozen in the ground, there's the potential that life could have existed in the past, or might exist today. This question, is there life on Mars, has captivated humanity for over a century, and we're closer than ever to finding an answer. The question is older than space travel itself. Is there life on Mars? For centuries, people have wondered whether the red planet might be home to living beings. In the late 1800s, astronomers using telescopes thought they saw straight lines crisscrossing Mars's surface. The Italian astronomer Giovanni Schiaparelli called them canali, which means channels in Italian, but the word was mistranslated into English as canals, implying artificial construction. The American astronomer Percival Lowell took this idea and ran with it, proposing that Mars was home to an advanced civilization that had built a planet-wide system of canals to transport water from the polar caps to the arid equatorial regions. This was, of course, fantasy. When spacecraft finally reached Mars in the 1,960 seconds and 70 seconds, they found no canals, no cities, no signs of intelligent life. The canali were optical illusions, tricks of light, and the human brain's tendency to see patterns where none exist. But the idea had captured imaginations worldwide. Even H.G. Wells's famous novel, The War of the Worlds, featured Martians invading Earth, though Wells portrayed them as hostile rather than benevolent. Mars had become synonymous with extraterrestrial life in popular culture. Today, we're not looking for Martians in the sense of intelligent beings. We're looking for microbes, or evidence that microbes once existed, and the search is not based on speculation or wishful thinking. It's grounded in solid scientific evidence that Mars was once a much more habitable world. Let's consider what life needs. At a minimum, life requires liquid water, a source of energy, and the right chemical elements. Water, as we've discussed, was abundant on early Mars. Energy. The sun provides energy everywhere on Mars's surface. So do chemical reactions in rocks and minerals. The chemical elements. Mars is made of the same stuff as Earth: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and trace elements. All the building blocks are there. Early Mars, during the Noachian period, about 4 billion years ago, probably had conditions suitable for life. The planet had a thicker atmosphere, warmer temperatures, and liquid water on its surface. Rivers flowed into lakes. Rain might have fallen. The environment would have been similar, in some ways, to early Earth. And we know life arose on Earth during a similar period. So if life emerged on Earth during its first billion years, why not on Mars too? This is the reasoning behind the search for past life on Mars. If we can find fossil evidence of ancient microbes or chemical biosignatures that can only be produced by living organisms, it would answer one of humanity's deepest questions. Are we alone in the universe? The first mission to directly search for life on Mars was Viking in 1976. NASA sent 2 landers, Viking 1 and Viking 2, each equipped with experiments designed to detect microbial life in Martian soil. These experiments were ingenious. One, called the Labeled Release Experiment, added nutrients containing radioactive carbon to soil samples. The idea was that if microbes were present, they would metabolize the nutrients and release radioactive carbon dioxide, which could be detected. And guess what? The experiment gave positive results. Gas was released, suggesting something was consuming the nutrients. But other experiments didn't support the presence of life. Most notably, the Gas Chromatograph Mass Spectrometer, GCMS, failed to detect any organic molecules in the fission, soil molecules that should be present if life existed or had ever existed there. The scientific consensus became that the Viking results were probably caused by exotic chemistry in the Martian soil rather than biology. Martian soil contains perchlorates and other oxidizing compounds that could produce the Viking results without any biology involved. Still, the Viking results remain controversial. Some scientists think Viking did detect life, and that we misinterpreted the results. It's possible that Martian microbes used different biochemistry than Earth life, or that organic molecules were present but destroyed by the reactive chemicals in the soil before the instruments could detect them. We may never know for certain what Viking detected, but the mission taught us an important lesson. Searching for life on Mars is complicated. Since Viking, no mission has directly searched for extant life. Instead, missions have focused on understanding Mars's habitability, whether the planet had environments that could support life, whether organic molecules are present, and whether water has played a role in shaping the planet. The strategy has been to follow the water, because where there's water, there's potential for life. The Mars rovers Spirit, Opportunity, Curiosity, and Perseverance have all found evidence that Mars once had environments suitable for life. Curiosity, which landed in Gale Crater in 2012, found evidence of an ancient lakebed. The minerals, the layered rocks, the rounded pebbles, all suggest that water once filled this crater, creating a lake that might have persisted for millions of years. Curiosity also detected organic molecules, complex carbon-based compounds that could be remnants of past life, or could have formed through non-biological processes. Either way, their presence is significant because it shows that the building blocks for life were present. Perseverance, which landed in Jezero Crater in 2021, is exploring what scientists believe was once a river delta, a place where a river emptied into a lake, depositing sediments. Deltas on Earth are often rich in organic material and are good places to look for fossils. Perseverance is collecting samples from this delta region, and these samples will eventually be returned to Earth by a future mission. When scientists can analyze those samples in sophisticated laboratories, we might finally get a definitive answer about whether life ever existed on Mars. Take a breath, slowly. Think about what it would mean if we found evidence of past life on Mars. It wouldn't just be a scientific discovery, it would fundamentally change how we see ourselves and our place in the cosmos. If life arose independently on two planets in the same solar system, it would suggest that life is common in the universe. Wherever conditions are right, life finds a way. But what about present life? Could there be living microbes on Mars today? The surface of Mars is harsh, cold, dry, bombarded by radiation. It's hard to imagine life surviving there, but beneath the surface, conditions might be different. If there's liquid water underground, if there are nutrients and a source of energy, microbes could potentially survive. They'd be isolated from the surface, shielded from radiation, living in a relatively stable environment. This is why astrobiologists are interested in accessing Mars's subsurface. Future missions might drill deep into the Martian crust, looking for signs of life in samples brought up from below. Or they might explore caves, where microbes could be protected from the harsh surface conditions, while still having access to nutrients from the rock. There's also the question of whether life could have been transported between Earth and Mars. This idea, called panspermia, suggests that microbes could hitch a ride on rocks ejected from one planet and eventually land on another. We know that Martian meteorites have reached Earth. We've found them and studied them. If rocks can travel from Mars to Earth, they can also go the other way. It's possible that life originated on one planet and spread to the other, making Earth life and Mars life distant relatives. This brings up an important consideration for future human missions: planetary protection. If there's life on Mars, we don't want to contaminate it with Earth microbes, and if there are Martian microbes, we don't want to bring them back to Earth without proper precautions. Spacecraft sent to Mars are carefully sterilized to reduce the number of Earth microbes hitching a ride. Samples returned from Mars will be handled in specially designed facilities to prevent any potential contamination. The search for life on Mars is one of the most exciting endeavors in modern science. It combines geology, chemistry, biology, and planetary science. It requires sophisticated instruments and carefully planned missions. And it asks a question that philosophers have pondered for millennia. Are we alone? We don't have an answer yet, but we're looking. Every rover that lands on Mars, every sample that's analyzed, every instrument that peers beneath the surface brings us closer to finding out. Maybe we'll discover unambiguous evidence of past life in the samples Perseverance is collecting. Maybe we'll find living microbes in a subsurface aquifer, or maybe we'll determine that Mars never had life, that Earth is unique in our solar system. Each answer would be profound in its own way. Finding life would tell us that biology is not a cosmic accident, that the universe is teeming with living things waiting to be discovered. Not finding life would make Earth seem even more precious, a rare oasis of biology in a cosmos that is, perhaps, mostly sterile. As you drift through these thoughts, imagine the scientists and engineers working on Mars missions. Imagine the rovers trundling across the Martian surface, sampling rocks, analyzing chemicals, searching for clues. Imagine the moment when someone examines data and realizes they're looking at evidence of extraterrestrial life. It would be a moment that divides human history into before and after, before we knew we weren't alone, and after. The search for life on Mars is really a search for our own origins, our own place in the universe. It's a question that goes beyond science and touches on philosophy, spirituality, and what it means to be human. And Mars, that rusty world wandering through the night sky, might hold the answer. Now let's turn our attention to something more tangible: the robots we've sent to Mars. These mechanical explorers have been our eyes and hands on another world, revealing Mars's secrets and paving the way for human exploration. Let's talk about the missions that have made Mars feel a little less distant and a little more real. Humans have not yet walked on Mars, but we've sent our proxies robots that can withstand the harsh environment, that don't need to breathe or eat, that can work for years, exploring the Martian landscape. These missions have transformed Mars from a distant point of light into a real place, a world we can study in detail. They've sent back hundreds of thousands of images, analyzed rocks and soil, measured the atmosphere and climate, and answered fundamental questions about Mars's history and potential habitability. The first successful mission to Mars was Mariner 4, which flew by the planet in 1965. It returned 22 images showing a cratered, moon-like surface, a disappointing result for those hoping to find a more Earth-like world. But it was a start. Over the following decades, multiple spacecraft have visited Mars, orbiters that circle the planet, mapping its surface, landers that settle gently onto the rust-colored plains, and rovers that can drive around exploring different locations. Let's talk about some of the most remarkable of these missions, starting with the rovers. In 1997, NASA landed a small rover called Sojourner as part of the Mars Pathfinder mission. Sojourner was about the size of a microwave oven and could only travel about 40 feet in a day, but it was the first rover on Mars, and it proved that the concept worked. For nearly 3 months, Sojourner analyzed rocks and soil, sending back data that revealed the composition of Martian materials. Then came Spirit and Opportunity, twin rovers that landed on opposite sides of Mars in January 2004. These rovers were much more capable than Sojourner, about the size of golf carts, equipped with sophisticated instruments and designed to last 90 days. Spirit operated for 6 years before getting stuck in soft sand and eventually succumbing to the cold Martian winter. Opportunity, incredibly, lasted almost 15 years, far exceeding its design life, before being silenced by that global dust storm in 2018. Spirit and Opportunity discovered some of the most compelling evidence that Mars once had liquid water on its surface. Opportunity found small spheres, nicknamed blueberries, concretions of hematite that likely formed in water. It also found layered rocks with cross-bedding patterns, indicating they were deposited by flowing water. Spirit found silica-rich deposits that probably formed in hot springs or volcanic vents surrounded by water. Both rovers revealed that Mars had a warmer, wetter past, a time when the planet might have been habitable. In 2012, NASA landed Curiosity, a rover the size of a small car, equipped with instruments that rivaled many Earth-based laboratories. Curiosity's mission was to explore Gale Crater and climb Mount Sharp, a mountain in the crater's center made of layered sedimentary rocks. The idea was that these layers recorded different environmental conditions over time, and by studying them, scientists could understand how Mars's climate changed. Curiosity has been incredibly successful. It found ancient streambed deposits, evidence of a long-lived lake, and organic molecules preserved in mudstones. It measured radiation levels on the surface, helping us understand the challenges astronauts will face. It's been analyzing the atmosphere, tracking seasonal changes in methane, which could have biological or geological origins, and even determining that Gale Crater once had conditions suitable for microbial life. Most recently, in February 2021, NASA landed Perseverance in Jezero Crater. Perseverance is similar to Curiosity in size and design, but it has a different mission: astrobiology. It's specifically looking for signs of ancient microbial life. Perseverance is equipped with instruments that can analyze the chemistry and mineralogy of rocks at a microscopic scale. It also carries a sample caching system. As it explores Jezero Crater, Perseverance is selecting the most interesting rocks, drilling into them, extracting cores, sealing those cores in tubes, and leaving the tubes on the Martian surface to be collected by a future mission. This sample return mission is years away, but it's one of the most anticipated endeavors in planetary science. When those samples finally reach Earth, scientists will be able to analyze them using instruments far more sophisticated than anything we can send to Mars. They'll be able to search for biosignatures, chemical or physical evidence of past life with unprecedented sensitivity. The samples could answer definitively whether life ever existed on Mars. Take a moment to appreciate what these rovers have accomplished. They're machines, yes, but they're also our avatars on another world. When you look at images from Curiosity or Perseverance, you're seeing through their cameras, seeing what they see. You're standing on Mars, in a sense, experiencing the rusty landscape, the distant horizon, the pink and butterscotch sky. The rovers make Mars tangible. And it's not just rovers. There are orbiters circling Mars right now, mapping the surface, studying the atmosphere, and serving as communication relays for the rovers below. NASA's Mars Reconnaissance Orbiter has a camera called HiRISE that can resolve features as small as about 3 feet across. It has returned some of the most stunning images of Mars, revealing avalanches cascading down polar slopes, dust devils marching across plains, and seasonal changes in polar ice. The European Space Agency has the Mars Express Orbiter and the Trace Gas Orbiter, both studying Mars's atmosphere and surface. India successfully sent its Mangalyaan orbiter to Mars in 2014, making India the first nation to reach Mars on its first attempt. The United Arab Emirates launched the Hope orbiter in 2020, which is studying Martian weather and climate. Mars has become a truly international destination, with multiple nations contributing to our understanding of the planet. China recently joined the ranks of nations that have successfully landed on Mars. In 2021, the Tianwen-1 mission arrived at Mars, consisting of an orbiter, a lander, and a rover named Zhurong. The mission successfully landed in Utopia Planitia, a vast plain in Mars's northern hemisphere, and Zhurong has been exploring the region, analyzing rocks and soil, and searching for evidence of ancient water. All these missions, the rovers, landers, and orbiters, are preparing the way for human exploration. They're teaching us about Mars's environment, helping us identify resources we can use, revealing hazards we'll need to address, and proving that we can operate reliably on another world. Each mission builds on the success of previous ones, gradually making Mars less alien and more accessible. But there have been failures too. Mars is a difficult target, and roughly half of all missions sent to Mars have failed. Orbiters have been lost, landers have crashed, rovers have gone silent. The Russians, in particular, have had a string of bad luck with Mars missions. The thin atmosphere makes landing especially tricky. There's enough air to create friction and heat, but not enough to slow spacecraft effectively with parachutes alone. Engineers have had to develop creative solutions, like inflatable airbags, sky cranes, and retro-rockets. Each failure is disappointing, but each teaches valuable lessons. Engineers analyze what went wrong, improve their designs, and try again. The history of Mars exploration is one of persistence, determination, and the gradual accumulation of knowledge. It's a reminder that exploring other worlds is hard, but not impossible. Let your mind wander back to those robots on Mars. Imagine Perseverance, Right now, as you lie here, trundling across Jezero crater, the sun is setting, or maybe rising, in that butterscotch sky. The rover is alone. The nearest humans millions of miles away. Its nuclear power source hums quietly, providing warmth and electricity. Its computer brain processes commands sent from Earth hours earlier, deciding where to drive, which rocks to examine. It's an ambassador from Earth, a pioneer, a testament to human curiosity and ingenuity, and it's paving the way for something even more ambitious: sending humans to Mars. The robots have done the reconnaissance, but eventually, if we're serious about making Mars a second home for humanity, we'll need to send people. That's the next chapter in our story: the dream, the challenge, and the reality of human Mars exploration. For as long as humans have known about Mars, we've dreamed of going there. The dream has taken many forms over the centuries: invasion fantasies, colonization schemes, scientific expeditions. But the core desire remains the same: to set foot on another world, to walk beneath an alien sky, to prove that humanity is not bound to a single planet. Today, that dream feels closer than ever to becoming reality. Multiple space agencies and private companies are working on plans to send humans to Mars. NASA's Artemis program aims to return humans to the Moon as a stepping stone to Mars. SpaceX, founded by Elon Musk, has the explicit goal of making humanity a multiplanetary species by establishing a self-sustaining city on Mars. Other nations, including China and the United Arab Emirates, have expressed interest in human Mars missions. But let's be clear: sending humans to Mars is vastly more difficult than sending robots. A human mission would require solving numerous challenges that don't apply to robotic missions. Humans need to breathe, eat, drink, and stay healthy. They need to be protected from radiation. They need to be able to return home, or at least, that's been the assumption for most mission plans. And all of this needs to happen over the course of months or even years, because the journey to Mars is long, and the launch windows only align every 26 months or so. Let's walk through what a human mission to Mars might look like, slowly and gently, considering each challenge as we go. First, the journey. Mars is, on average, about 140 million miles from Earth. At the closest approach, it's about 34 million miles away. But you can't simply point a spacecraft at Mars and fly directly. You have to follow an orbital trajectory that conserves fuel. The most efficient path is called a Hohmann transfer orbit. A spacecraft launched from Earth accelerates and enters an elliptical orbit around the Sun. At the right time, this orbit intersects with Mars's orbit, and the spacecraft can perform a final burn to enter orbit around Mars or descend to the surface. This journey takes about 6 to 9 months, depending on the specifics of the trajectory and the propulsion system used. That's a long time to spend in a confined space, far from Earth, with no possibility of quick rescue if something goes wrong. Astronauts would need to bring everything they need for the entire journey: food, water, air, tools, spare parts, medical supplies. The spacecraft would essentially be a miniature habitat drifting through the void. One of the biggest challenges is radiation. In space, beyond Earth's protective magnetic field, astronauts are exposed to cosmic rays and solar radiation. Cosmic rays are high-energy particles, mostly protons, that zip through space at nearly the speed of light. They can penetrate spacecraft hulls and human bodies, damaging DNA and increasing cancer risk. Solar radiation, particularly during solar storms, can also be dangerous. How do we protect astronauts from radiation? There are several approaches. One is shielding surrounding the spacecraft with thick walls of material that can absorb radiation. Water, hydrogen-rich plastics, and even regolith, soil, from Mars, could serve as shielding. But thicker walls mean more mass, and every kilogram of mass increases fuel requirements and cost. Another approach is to minimize exposure time by using faster propulsion systems, though developing such systems is a major engineering challenge. Some propose that astronauts could take shelter in a specially shielded area of the spacecraft during solar storms, which are somewhat predictable. Others suggest using electromagnetic or plasma fields to deflect charged particles. Though this technology is still largely theoretical, the truth is, radiation is a significant risk, and any human Mars mission will need to accept some level of elevated cancer risk for the crew. Then, there's the psychological challenge. Being confined in a small spacecraft with a handful of other people for months on end, knowing that Earth is getting farther away and help is impossible, could be mentally taxing. Isolation, monotony, lack of privacy, interpersonal conflicts, all of these could affect crew performance and well-being. Mission planners study analogues, like Antarctic research stations and submarines, to understand how people cope with isolation and confinement. They're developing strategies for crew selection, training, and support to maximize the chances of psychological health. Throughout the mission, upon arriving at Mars, the crew would face the challenge of landing. Mars's thin atmosphere makes landing heavy payloads tricky. Parachutes alone aren't sufficient, so you need retrorockets. But retrorockets require fuel, adding more mass. Landing a spacecraft large enough to house humans, along with all their supplies, is a major engineering hurdle. NASA and other agencies are working on technologies like supersonic retropropulsion, which fires rockets while the spacecraft is still traveling at supersonic speeds, to slow it down more effectively. Once on the surface, astronauts would need a habitat. This could be a pre-deployed structure sent ahead of the crew, something they inflate after landing, or a rigid module similar to those on the International Space Station. The habitat would need to provide life support, recycling air and water, managing waste, producing food. It would need to protect against radiation, using either thick walls or burial under Martian regolith. It would need to maintain a comfortable temperature despite the extreme cold outside. Living on Mars would be strange. The reduced gravity, 38% of Earth's, would make movements feel different. You'd be lighter, but also clumsier, at least at first. Studies on astronauts returning from long-duration missions on the International Space Station show that reduced gravity causes muscle atrophy and bone density loss. Exercise regimens can mitigate this, but it's unclear how the human body would adapt to Mars's gravity over months or years. Take a breath. Imagine yourself as one of the first astronauts on Mars. You wake up in your small sleeping compartment. The habitat is quiet except for the hum of life support systems. You put on your spacesuit, a process that takes at least 30 minutes, and step outside. The sky is its usual butterscotch hue. The sun is smaller than it appears from Earth, about 2/3 the size. The landscape stretches out before you, rust red and rocky. You take a step, and you bounce slightly. Not quite used to the lower gravity. You're standing on Mars. What would you do? Probably scientific work, collecting samples, setting up experiments, maintaining equipment. But there would also be mundane tasks. Checking solar panels, repairing anything that broke, cooking meals, exercising to maintain bone and muscle mass. Life on Mars would be a mix of the extraordinary and the routine. And then there's the question of returning home. A Mars mission could be a round trip, with the crew returning to Earth after a year or so on the surface. Or it could be a one-way trip, with the goal of establishing a permanent settlement. Both approaches have been proposed, and both have their advocates. A round-trip mission requires carrying enough fuel to launch from Mars and return to Earth, or producing that fuel on Mars using local resources. Mars's atmosphere is mostly carbon dioxide, and there's water ice in the ground. Using a process called the Sabatier reaction, you can combine carbon dioxide and hydrogen to produce methane and water. Methane can be used as rocket fuel. This process, called in situ resource utilization, ISRU, would significantly reduce the mass that needs to be launched from Earth. A one-way mission, on the other hand, is simpler in some ways. You don't need return fuel, so the spacecraft can be lighter. The crew commits to staying on Mars, either permanently or until a later mission can bring them home. The Mars One project, proposed in the early 2010 seconds, envisioned a one-way trip to establish a permanent colony, though the project ultimately failed due to financial and technical challenges. Still, the idea persists that the first humans to Mars might stay there, becoming the founders of a new branch of human civilization. What would motivate someone to make a one-way trip to Mars? For some, it's the adventure, the chance to be part of history. For others, it's the scientific opportunity living on Mars would allow for research that's impossible with robots. And for some, it's philosophical, the belief that humanity's manned philosophical future lies beyond Earth, that we need to become a multi-planetary species to ensure our long-term survival. Let's pause and consider that idea. Earth is our cradle, but it's also vulnerable. Asteroid impacts, supervolcanic eruptions, nuclear war, climate change. There are numerous scenarios that could make Earth uninhabitable or drastically reduce the human population. Having a second home on Mars would be an insurance policy, a way to ensure that even if something catastrophic happens to Earth, humanity survives somewhere. This is the argument that drives much of the current enthusiasm for Mars colonization. People like Elon Musk speak about making life multiplanetary not just as a scientific goal, but as an existential necessity. If we stay confined to Earth, we risk extinction. If we spread to other worlds, we become resilient. But is Mars really suitable as a backup for Earth? That's a question worth pondering as you drift towards sleep. Mars is cold, dry, has a thin atmosphere, and lacks a magnetic field. It has resources, yes, water ice, carbon dioxide, minerals, but making Mars habitable would require a massive, sustained effort. Would it be easier to fix problems on Earth than to terraform Mars? Perhaps, but there's also the argument that developing the technology to live on Mars would benefit Earth as well, by advancing renewable energy, recycling systems, and sustainable living practices. The dream of Mars is not just about escaping Earth. It's about expanding our horizons, about proving that humans can adapt to any environment. It's about curiosity, the same curiosity that led our ancestors to explore Earth's continents and oceans. Mars is the next frontier, the next challenge, the next step in the human journey. And maybe, just maybe, it's about wonder, about standing beneath an alien sky and realizing that the universe is vast, that there are places beyond our small blue world, that we're capable of reaching out and touching them. Mars represents possibility. It's a place where humanity can write a new chapter, where the future is unwritten and full of potential. As you imagine those first footsteps on Martian soil, as you think about the habitats and rovers, the challenges and dreams, let yourself feel the weight of it all, and then let it go. Let your thoughts drift like dust across the Martian plains, soft and weightless. We're not done with our journey yet. There's one more big idea to explore: terraforming. The question of whether we can transform Mars into a more Earth-like world, turning it from a frozen desert into a place where humans could walk without spacesuits, where liquid water flows freely, where life could thrive. That's where we're heading next, slowly and gently. What if we could change Mars? Not just build habitats and survive there, but actually transform the planet itself, making it warmer, giving it a thicker atmosphere, bringing liquid water back to its surface? This idea is called terraforming, literally Earth shaping, and it's one of the most ambitious concepts in all of science and engineering. Terraforming Mars would be a project spanning centuries, perhaps millennia. It would require resources on a scale that's hard to comprehend, But it's not impossible. The laws of physics don't forbid it. It's a matter of engineering, energy, and time. Let's explore, slowly and carefully, how terraforming might work and what challenges it would face. The goal of terraforming is to create conditions on Mars that are more Earth-like. Specifically, we'd want to raise the temperature so that water can exist as a liquid on the surface, thicken the atmosphere so that liquid water is stable and so that humans could eventually breathe without assistance, potentially create a magnetic field to protect the atmosphere from being stripped away by solar wind, introduce life, plants, microbes, perhaps eventually animals, to create a self-sustaining ecosystem. Let's start with temperature. Mars is cold because it's farther from the sun than Earth, and because its thin atmosphere can't trap heat effectively. To warm Mars, we need to increase the greenhouse effect. Greenhouse gases like carbon dioxide, water vapor, and methane trap heat by absorbing infrared radiation that would otherwise escape to space. Mars's atmosphere is already mostly carbon dioxide, but it's so thin that the greenhouse effect is weak. One proposed method for warming Mars is to deliberately increase greenhouse gases in the atmosphere. Where would these gases come from? There are several possibilities. Mars's polar caps contain frozen carbon dioxide. If we could warm the poles, this dry ice would sublimate, adding carbon dioxide to the atmosphere. More carbon dioxide means a stronger greenhouse effect, which leads to more warming, which releases more carbon dioxide from the poles. It's a positive feedback loop. How do we start this process? One idea is to use orbital mirrors, large, thin mirrors positioned in orbit around Mars to reflect sunlight onto the polar caps. The mirrors wouldn't need to be particularly massive. They could be made of ultra-thin, reflective material. By concentrating sunlight on the poles, they would gradually warm the ice, releasing carbon dioxide. Another idea is to spread dark material soot or engineered particles on the ice. Darker surfaces absorb more sunlight, so coating the poles in dark material would increase the amount of solar energy absorbed. A more ambitious idea involves redirecting comets or asteroids to impact Mars. These icy bodies contain water and, in some cases, ammonia. Impacts would vaporize the ice, adding water vapor and other greenhouse gases to the atmosphere. The heat from the impacts would also warm the surface. This is a spectacular idea, though the engineering challenges and risks are enormous. You'd need to carefully calculate trajectories and make sure you're not accidentally destroying important scientific sites or future habitats. Another proposal involves building factories on Mars to produce super greenhouse gases molecules that are far more effective at trapping heat than carbon dioxide. Perfluorocarbons, PFCs, for example, are thousands of times more effective as greenhouse gases than CO2. Releasing even small amounts into the Martian atmosphere could have a significant warming effect. The downside is that producing these gases would require energy and raw materials, and we'd need to establish a substantial industrial base on Mars first. Take a moment to imagine this. Slowly, over decades, Mars begins to warm. The polar caps start to sublimate, and carbon dioxide fills the atmosphere. The atmospheric pressure increases. The greenhouse effect strengthens. Temperatures rise, first at the poles, then spreading toward the equator. At some point, the temperature reaches above the freezing point of water, and ice begins to melt. Now water is flowing on Mars again, for the first time in billions of years. Streams trickle down from the highlands, lakes form in craters. Perhaps, if we're very successful, a shallow sea begins to fill the northern lowlands, recreating the ancient ocean that might have existed there in Mars's youth. This would be a world transformed, a planet reborn. But thickening the atmosphere and warming the planet is just the first step. The atmosphere would still be mostly carbon dioxide, which humans can't breathe. To make Mars truly habitable, we'd need to change the atmospheric composition. increasing oxygen levels to the point where humans could breathe unaided. How do we do this? The answer is life. On Earth, it was photosynthetic organisms. First, cyanobacteria, later plants that produce the oxygen in our atmosphere. Life transformed Earth's atmosphere from one dominated by nitrogen, carbon dioxide, and methane into one with 21% oxygen. The same process could work on Mars, though it would take a long time. We could introduce photosynthetic microbes hardy, extremophile versions of cyanobacteria or algae engineered to survive on Mars. These organisms would use sunlight to convert carbon dioxide and water into organic matter and oxygen. Over centuries, as they multiplied and spread across the planet, they would gradually increase oxygen levels and reduce carbon dioxide. Eventually, we might introduce plants. Once there's enough atmosphere and liquid water, plants could grow in the Martian soil, perhaps with some amendments to make it less toxic. Forests, grasslands, and other ecosystems could slowly transform Mars into a green world. This process would take hundreds or thousands of years, but the endpoint would be a planet with a breathable atmosphere, a living biosphere, and a climate capable of sustaining complex life. Of course, there are challenges. One is the lack of a magnetic field. As we discussed earlier, Mars lost its global magnetic field billions of years ago, and without it, the solar wind can strip away the atmosphere. Terraforming Mars, only to have the new atmosphere gradually erode away, would be frustrating, to say the least. Is there a solution? Some scientists have proposed creating an artificial magnetic field. One idea is to place a magnetic dipole, a large electromagnet, at the L1 Lagrange point between Mars and the Sun. This point is where the gravitational pull of Mars and the Sun balance out. An electromagnet at this location could generate a magnetic field that shields Mars from the solar wind, allowing a thickened atmosphere to persist. This sounds like science fiction, but the physics is sound. The challenge is engineering, building a magnet powerful enough to create a field that large, and positioning it precisely at the L1 point. It would require advanced technology, substantial resources, and a long-term commitment. But it's not impossible. Let your mind drift over this terraformed Mars. Imagine a world centuries from now. The sky is no longer butterscotch. It's a pale blue, though not as vibrant as Earth's. Clouds drift overhead, real clouds of water vapor, perhaps even producing rain. The temperature at the equator on a summer day is comfortably warm. You can see green patches on the landscape, lichen, moss, perhaps even small shrubs. Rivers flow from the highlands to the lowlands. There's a shallow sea in the north, its waters cold but liquid, lapping against rust-colored shores. You're standing there without a spacesuit. The air is thin, about the same pressure as being at the top of a high mountain on Earth, but with enough oxygen that you can breathe, albeit with some difficulty. Humans have adapted, or perhaps they've been genetically modified to be more efficient at extracting oxygen from thin air. This is a world where humans live not in enclosed habitats, but in open-air settlements, farming the land, building cities, raising children who will never see Earth, but who will think of Mars as home. Is this future realistic? That depends on many factors: technological capability, economic resources, political will, and the ethical implications of transforming an entire planet. Terraforming Mars would be the largest engineering project in human history, dwarfing anything we've done on Earth. It would cost trillions of dollars and require cooperation across nations and generations. And it raises profound ethical questions. Do we have the right to transform Mars? Some argue that Mars is a pristine scientific laboratory, and we should preserve it as it is for study. If there's any chance that life exists on Mars, even just dormant microbes beneath the surface, do we risk contaminating or destroying it by introducing Earth life? Others argue that Mars is lifeless now, and that transforming it into a living world is a moral good, expanding the sphere of life in the universe. There's also the question of practicality. Even with all our technology and effort, would a terraformed Mars be as livable as Earth? Probably not. The gravity is still only 38% of Earth's, which might have health implications over generations. The day-night cycle is similar, which is good, but the seasons are longer and more variable. Mars would likely remain a colder, drier, less hospitable version of Earth. It would be a second home. Yes, but not a duplicate of our first. Take a breath. Let these thoughts settle. Terraforming is a dream, a vision of what might be possible if humanity commits to the long-term challenge of making Mars habitable. It's not something that will happen in our lifetimes, or even our children's lifetimes, but it's a reminder that we're not bound by the conditions we find. We can adapt environments, not just adapt to them. Whether or not we ultimately choose to terraform Mars, the idea serves a purpose. It forces us to think deeply about our relationship with other worlds, about the limits and possibilities of technology, about what kind of future we want to create. It's an exercise in imagination and ambition, a way of dreaming on a planetary scale, and perhaps that's fitting for Mars, a planet that has always inspired dreams, from ancient astronomers naming it after a god of war, to Percival Lowell imagining canals, to science fiction writers envisioning colonies and civilizations. Mars has been a canvas for human imagination. Terraforming is just the latest chapter in that long story, a dream of transforming the red planet into a green one, of bringing life to a world that might once have had its own. As we drift toward the end of our journey together, let's pause and reflect on everything we've explored. Mars, the red planet, our neighbor in space, a world with a rich history, from its wet and possibly habitable past to its cold, dry present, a world that has captured human imagination for centuries and that now stands as the most likely destination for humanity's expansion beyond Earth. We've one more section to explore, a look at the current missions, near-future plans for Mars, the stepping stones that will take us from robotic exploration to human presence. Let's gently make our way there, considering what comes next in humanity's relationship with Mars. So where are we now in our relationship with Mars? What are the next steps? And what might the coming decades hold? Let's wander through the current state of Mars exploration and the plans that are taking shape, slowly and thoughtfully, considering each piece of the puzzle. As of now, Mars is a remarkably busy place, at least by the standards of planetary exploration. There are multiple rovers on the surface, several orbiters circling overhead, and more missions on the way. This sustained presence represents a level of commitment to Mars exploration that would have seemed like science fiction just a few decades ago. NASA's Perseverance rover, which landed in 2021, continues its mission in Jezero Crater. As we mentioned earlier, it's collecting samples that will eventually be returned to Earth. This sample return mission is a complex, multi-phase endeavor. After Perseverance collects and caches samples, a future mission currently planned for the late 2022 or early 2030 will land on Mars, retrieve the sample tubes, launch them into orbit around Mars, and then transfer them to a spacecraft that will carry them back to Earth. This Mars Sample Return, MSR, mission is one of the highest priorities in planetary science. The samples could contain evidence of past life, detailed records of Mars's geological history, and information about the planet's past climate and habitability, having Martian rocks and soil in Earth laboratories, where they can be analyzed with instruments far more sophisticated than anything we can send to Mars, would be transformative for our understanding of the red planet. NASA is also planning the next generation of Mars missions. One concept under development is the Mars Ice Mapper mission, which would use radar to map subsurface ice in greater detail than ever before. Knowing exactly where water ice is located and how deep it is would be crucial for planning human missions. Another concept is a helicopter-like drone that could explore places rovers can't reach: cliffs, caves, and canyon walls. China has ambitious plans for Mars as well. Following the success of the Tianwen-1 mission, China is planning to conduct its own Mars sample return mission, possibly before NASA and ESA complete theirs. China also has expressed interest in eventually sending astronauts to Mars, though no specific timeline has been announced. The country's space program has been advancing rapidly, and it's likely that future Mars exploration will be increasingly international. The European Space Agency, ESA, in collaboration with Roscosmos, Russia's space agency, is working on the ExoMars program. This program includes a rover named Rosalind Franklin, equipped with a drill that can reach up to 6.5 feet below the surface, deeper than any previous Mars rover. The goal is to search for biosignatures in subsurface samples, where organic molecules might be better preserved. The mission has faced delays, partly due to geopolitical tensions, but remains a priority for ESA. Private companies are also getting involved. SpaceX, as we've mentioned, has the explicit goal of establishing a human presence on Mars. The company is developing the Starship spacecraft, a fully reusable launch system designed to carry cargo and eventually people to Mars. Starship is massive, much larger than any rocket currently flying, and if successful, it could dramatically reduce the cost of sending payloads to Mars. Elon Musk has spoken about creating a self-sustaining city on Mars with a population of 1 million people. This is an audacious vision, and it remains to be seen whether it's realistic. But SpaceX is making progress on the technology. Starship prototypes have conducted test flights, and the company is iterating rapidly on the design. If Starship becomes operational, it would be a game changer for Mars exploration and colonization. Take a breath. Think about the timescale of all this. In the 2030 seconds, we might see the first humans orbit Mars or land on its surface. By the 2040 seconds or 2050 seconds, there could be a permanent base, with crews rotating in and out every couple of years. By the end of the century, if things go well, there could be settlements with thousands or tens of thousands of people. Mars would transition from a scientific destination to a frontier, a place where people live and work and build new societies. But let's not get too far ahead. There are still enormous challenges to overcome. One is the question of long-term health effects. We've learned a lot from astronauts spending months on the International Space Station, but Mars presents additional challenges. The journey to Mars exposes astronauts to radiation. Living on Mars subjects them to lower gravity, which might cause long-term bone and muscle loss. Returning to Earth after a year or more on Mars could be difficult, as the body readapts to Earth's higher gravity. Some have proposed that the first Mars colonists might never return to Earth, not because it's impossible, but because readapting would be too difficult. Their bones and muscles, adapted to Martian gravity, might not support their weight on Earth. This raises ethical questions. Should we send people to Mars, knowing they might not be able to come back? Is it fair to ask people to make such a sacrifice? Another challenge is sustainability. A Mars colony would need to be as self-sufficient as possible, because resupply missions from Earth would be expensive and infrequent. Colonists would need to produce their own food, recycle water and air, manufacture tools and spare parts, and generate energy. This requires developing closed-loop life support systems, reliable agricultural methods, and in-situ resource utilization technologies. Food production on Mars is particularly interesting. You can't grow crops in Martian soil without modification. It's salty, contains toxic perchlorates, and lacks organic matter. But with some processing, it could be made arable. Greenhouses with controlled environments could produce vegetables and other crops. Hydroponics and aeroponics methods of growing plants without soil could be highly efficient in the low-gravity environment. Energy would come primarily from solar panels, at least initially. Mars receives about 44% as much sunlight as Earth, so solar panels would need to be larger and more efficient. Nuclear power is another option. Small modular reactors could provide reliable energy, regardless of dust storms or the day-night cycle. Both approaches are being developed and tested. The psychological and social aspects of colonization are also important. What kind of society would develop on Mars? Would it be an extension of Earth's cultures, or would it develop its own identity? Living on Mars would be challenging. People would spend most of their time indoors. Communication with Earth would have a delay of 4 to 24 minutes each way, depending on the planet's positions, making real-time conversations impossible. Children born on Mars, and there will be children if we establish permanent settlements, would grow up in an environment radically different from Earth. They'd adapt to the lower gravity, and they might never be able to visit Earth because their bodies wouldn't handle Earth's stronger gravity. Martian-born humans could represent the first generation of a truly multiplanetary humanity. People whose homeworld is not the blue marble we came from, but the red world we've chosen to inhabit. There's something both exciting and melancholy about that thought. Exciting because it represents humanity taking a genuine step toward becoming a spacefaring civilization. Melancholy because it means separation, distance, the slow divergence of Earth and Mars cultures over generations. But perhaps that's simply the nature of exploration and expansion. Cultures on Earth diverged as humans spread across continents. The same might happen as we spread across planets. Let's pause and think about cooperation. Mars exploration and colonization will require unprecedented levels of international cooperation. No single nation has the resources to establish a permanent Mars presence alone. Space agencies are already collaborating, NASA and ESA, on the Mars Sample Return mission. For example, future missions will likely involve even more partnerships, with different nations contributing different capabilities: launch vehicles, habitats, life support systems, scientific instruments. Private companies add another dimension to this cooperation. SpaceX might provide transportation, while other companies develop habitats, mining equipment, or agricultural systems. The Mars economy, if it develops, would be a mix of public and private entities working together toward common goals. This blend of competition and cooperation could drive innovation and efficiency. There are also legal and governance questions. Who owns Mars? Under the Outer Space Treaty of 1967, no nation can claim sovereignty over celestial bodies. Mars belongs to all of humanity, in principle, but as colonization becomes a reality, questions of property rights, resource extraction, and governance will need to be addressed. Will Mars colonies be governed by Earth-based authorities, or will they develop their own systems of self-governance? History suggests that frontiers develop their own institutions and eventually seek autonomy. The American colonies were originally governed by Britain, but eventually declared independence. Might Mars colonies follow a similar path? It's an intriguing thought. Perhaps centuries from now, Mars will be an independent world, with its own government, economy, and culture, maintaining ties with Earth, but charting its own course. As you let your thoughts drift through these possibilities, imagine the long view, not just the next few decades, but the next few centuries. Mars is not just a destination for a handful of missions. It's a place where humanity might build a lasting presence, where new chapters of human history will be written. Every mission we send, every rover that lands, every sample that's analyzed is a step toward that future. And the path forward is becoming clearer. We have the technology to reach Mars. We have rovers exploring its surface and orbiters mapping it from above. We're learning how to use Martian resources, water ice, carbon dioxide, minerals to support human presence. We're developing the life support systems, radiation shielding, and propulsion technologies needed for long-duration missions. The pieces are coming together. The question is no longer, can we go to Mars? But rather, when will we go? And how quickly can we establish a sustainable presence? Different groups have different timelines, different approaches, different visions. But the direction is clear. Humanity is going to Mars. The red planet will be explored, studied, and probably settled within the next few decades. This is one of the most exciting times in the history of space exploration. We're on the cusp of becoming a multi-planetary species. We're about to take the lessons learned from robotic missions and apply them to human exploration. We're preparing to write the next great chapter in the human story. The chapter where we leave our cradle world and reach out to touch another. And yet, amid all this excitement, it's important to remember the gentle pace of progress. Space exploration moves slowly. It takes years to plan missions, build spacecraft, and travel to Mars. It will take decades to establish a permanent presence, longer still to make Mars truly habitable. This is not a sprint but a marathon, a multi-generational project that requires patience, persistence, and vision. As we near the end of our journey together, let's take one last look at Mars through the lens of wonder, not as a scientific challenge or a destination for colonization, but simply as a world, beautiful, strange, and full of mysteries. Let's appreciate Mars for what it is, a planet with its own history, its own landscape, its own story to tell. There's something quietly beautiful about Mars. It's not the lush beauty of Earth, with its blue oceans and green forests. It's a different kind of beauty, the beauty of stark landscapes, of geological time laid bare, of a world shaped by forces that have played out over billions of years. Imagine the view from the rim of Valles Marineris at sunset. The canyon walls, layered in shades of red, orange, and brown, catch the fading light. Shadows deepen in the valleys below. The sky transitions from butterscotch to deep blue grey, and stars begin to appear, more stars than you'd see from Earth, because Mars's thin atmosphere scatters less light. The sun sets, not in a blaze of red and orange like on Earth, but with a quiet blue glow around its disk, a consequence of how dust particles scatter light in the Martian atmosphere. Or picture a dust storm seen from orbit. The storm begins as a small disturbance, a swirl of dust lifted by wind. Over days, it grows, spreading across plains and over mountains, gradually enveloping half the planet. From above, Mars transforms, its normally varied terrain becoming a uniform amber haze. And then, slowly, the storm dissipates. The dust settles, revealing the landscape once more, perhaps subtly changed, with new dunes formed and old ones erased. Think about the polar caps in spring. As temperatures rise, the carbon dioxide ice begins to sublimate. Sometimes it doesn't sublimate evenly. Gas trapped beneath translucent ice can build up pressure and then burst through, carrying dark sand with it. The result is features that look like dark spiders, dendritic branches spreading across the white ice patterns that appear almost organic, as if the ice itself is alive and growing. Mars has quiet grandeur. It's not loud or flashy. It doesn't demand attention with vivid colors or dramatic weather. Instead, it offers subtlety, the slow procession of seasons, the patient work of wind and sublimation, the ancient record of water, written in stone. It's a planet for contemplation, for those who appreciate the beauty of geology and time. Consider the rocks that litter the Martian surface. Each one is a story. Some are volcanic, formed from molten rock that erupted from the depths billions of years ago. Others are sedimentary, made of particles deposited by wind or water and compacted over eons. A few are meteorites, fragments of other worlds that happen to fall on Mars. The rovers have studied hundreds of these rocks, each one adding a small piece to the puzzle of Mars's history. There's poetry in dust. Martian dust is everywhere, coating rocks, filling cracks, blowing across plains. It's fine as talcum powder, rust red in colour, rich in iron oxide. When wind lifts it into the air, it creates those characteristic dust storms. When it settles, it forms dunes and ripples, patterns that shift slowly over the years. The dust is both a nuisance coating solar panels, obscuring views, and a marvel, a reminder that Mars is still active, still changing, still very much a living planet in the geological sense. Let's think about time on Mars. A Martian year is 687 Earth days. A Martian day is 24 hours and 37 minutes. If you lived on Mars, your calendar and clock would gradually drift out of sync with Earth's. Holidays, anniversaries, birthdays, they'd all occur at different times relative to Earth. After a few years, Christmas might fall in Martian summer. Your birthday might drift through all 4 Martian seasons over the course of a few Earth decades. There's something gently disorienting about that. It's a reminder that Mars is its own world, with its own rhythms and cycles, not just an extension of Earth. Living on Mars would mean adapting not just to the physical environment, but to a different relationship with time itself. And speaking of seasons, imagine the first rain on Mars. If we successfully terraform the planet, there would come a moment when the atmospheric pressure and temperature rise enough that water vapor in the air begins to condense into droplets. The first clouds would form, wispy at first, then thicker, and then, perhaps on a spring day in some future century, rain would fall, droplets of water, falling through Martian air, landing on Martian soil for the first time in billions of years. It would be one of the most profound moments in planetary history, the return of the water cycle to a world that once had it and lost it. Take a breath, let that image settle. Rain falling on Mars. It's such a simple thing, something we take for granted on Earth. But on Mars, it would be a miracle, the culmination of centuries of effort and the beginning of a true transformation. There's also beauty in the small details, the way frost forms on rocks during winter nights, creating intricate patterns of ice crystals, the way shadows lengthen as the sun arcs across the sky, moving more slowly than on Earth, because the Martian day is slightly longer, the way Phobos, the larger moon, races across the sky, rising in the west and setting in the east, just a few hours later, the way stars don't twinkle in the thin atmosphere, but shine with steady, unwavering light. Mars is a world of contrasts, ancient and yet changeless, dry and yet holding vast reserves of ice, barren and yet potentially habitable, dead and yet perhaps not quite lifeless. It exists in a state of potential, waiting for the next chapter of its story to unfold. And in a way, Mars reflects something about humanity itself. We're explorers, dreamers, tool makers. We look at a cold, hostile world and see not just obstacles but possibilities. We ask not, can we survive there, but how can we thrive there? This impulse to explore, to push boundaries, to reach for the impossible, it's deeply human. Mars is the current focus of that impulse, but it won't be the last. Beyond Mars lie the asteroids, the moons of Jupiter and Saturn, eventually perhaps other star systems. Mars is just the beginning. But for now, it's enough. Mars is enough. It's close enough to reach, fascinating enough to study, challenging enough to test our capabilities, and hospitable enough that we might, with effort, make it a second home. It's the perfect next step in humanity's journey beyond Earth. As you lie there, breathing slowly, let your mind wander one last time across the Martian landscape, the rust-red plains, the towering volcanoes, the yawning canyons, the spiral polar caps. the hidden ice beneath the surface, the thin wind that never stops blowing, the pink butterscotch sky, the distant, shrunken Sunday, the two tiny moons, the silence, oh, the profound silence of a world without oceans, without rain, without life making noise. Mars is waiting, not just for our robots and astronauts, but for our imaginations, our dreams, our hopes for the future. It's been waiting for billions of years, and it will wait a bit longer. But someday, perhaps someday soon, humans will stand on that rusty soil, look up at that alien sky, and call Mars home. And in that moment, we will have become something new, a species that lives on two worlds, a civilization that has taken its first real step into the cosmos. Mars will cease to be merely a destination and will become a place with its own stories, its own memories, its own meaning in the human experience. This is the promise of Mars. This is the dream that drives us forward, and this is where our gentle journey together reaches its quiet conclusion. So, what is Mars, really? It's the question that brought us here. Whispered softly at the beginning like a child, asking if there are other worlds we might one day visit. And after wandering through its ancient history, its geological wonders, its vanishing atmosphere, its hidden waters, and its potential as a future home, we find ourselves gently circling back to where we began, still wondering, but now with deeper understanding. We've learned that Mars is not just a planet, but a world with a story, a world that once had flowing rivers and perhaps ancient oceans, that lost its magnetic field and then its atmosphere, that transformed over billions of years from a warm, wet place into the cold, dry desert we see today. We've explored how Mars is both familiar and alien, with seasons and polar caps like Earth, but also with a butterscotch sky and gravity that's just a fraction of what we're used to. We've discovered that Mars is not quite dead, not quite alive, but something in between, dormant, perhaps waiting. We've considered the search for life, both past and present, and the profound implications of finding even a single fossil microbe. We've marveled at the robots we've sent to Mars, our mechanical pioneers that have revealed so much about this distant world, and we've dreamed about the future, about human footsteps on Martian soil, about settlements and terraforming, about Mars becoming a second home for humanity. Maybe Mars doesn't need to give us all the answers. Maybe it's enough that it asks such fascinating questions. Maybe the real value of Mars is not what we find there, but what the journey of exploration reveals about ourselves. Our curiosity, our resilience, our ability to dream beyond the boundaries of our home world. Maybe that's the whole point. The universe doesn't owe us easy answers or simple destinations. It simply exists, vast and full of mysteries, inviting us to explore. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though, if I was, well, at least you've learned a few things about Mars along the way. You know now about its rust-coloured dust, its towering Olympus Mons, its grand Valles Marineris, its hidden ice reserves, and its potential as humanity's next frontier. And if you're already halfway to dreamland, may your thoughts drift gently across Martian plains, beneath that pink butterscotch sky, where dust storms whisper and ancient rivers once flowed. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perhaps an astronomy student dreaming of Mars missions? Or someone who simply finds the red planet strangely comforting? Are you watching from Earth, looking up at Mars as a distant point of red light in your night sky? Or are you listening in the middle of the day, letting your mind wander to distant worlds while the sun shines outside your window? If you found this gentle journey to Mars relaxing or informative, or both, please do consider giving this video a like and subscribing to sleepy science student. It's a small gesture that helps me keep bringing you more calming, curious content from the worlds of science and space exploration. Your support means I can continue to create these peaceful voyages through the cosmos, one fascinating topic at a time. Thank you for joining me on this journey to the Red Planet. Sleep well, dream deep, and may you find yourself standing on Martian soil in your dreams, looking up at two tiny moons in an alien sky. Remember, somewhere among the stars, Mars is spinning quietly through space, waiting patiently for us to arrive. You don't need to rush toward it tonight. Just let yourself float gently towards sleep, carried on the thin Martian wind, surrounded by the quiet beauty of a world that might one day be home. Good night.